that tracks targets and engages them by combining 6 high-energy lasers.
A US Navy laser reaches its target at the speed of light. Killing with it takes several sustained seconds on a target through maritime air that actively works to defocus and scatter the energy. The drone is not the hard part. The atmosphere between the ship and the target is. The physics of laser weapons has been understood since 1960. The reason it took 6 decades to put one on a ship has nothing to do with the laser and everything to do with what happens to the beam after it leaves the aperture. The first high-energy laser programs identified 3 problems that had to be solved simultaneously before a laser could function as a deployable naval weapon: generating enough power at the required beam quality, removing the waste heat that power generation produced before it degraded the output, and getting that energy through an atmosphere that treated every kilometer between the ship and the target as an optical obstacle. Solving any one in isolation produced laboratory results that did not transfer to an operational system. Each solution interacted with the other 2 in ways that made partial progress nearly irrelevant. Increasing power increased the waste heat load. Improving the cooling system consumed the weight and power budget available for additional laser modules. Neither advance moved the beam through the air any better. All 3 problems had to fall simultaneously in a package compact and rugged enough to survive shipboard conditions, salt air, constant vibration, and the electrical supply constraints of a warship underway. The AN/SEQ-3 laser weapon system uses solid-state fiber laser technology, specifically a method called spectral beam combining, which merges multiple lower-power laser modules into a single coherent output beam without sacrificing the beam quality that makes the combined output lethal at range. Each module generates a beam at a slightly different wavelength. A combining optical element overlaps those beams into a single propagation path, and the result behaves as a single coherent source carrying the total power of all contributing modules. The AN/SEQ-3 draws on approximately 6 fiber laser modules, roughly the number of starting players on a volleyball court, combined into an output in the 30 kilowatt range. Each module is individually serviceable. If one degrades, and the system loses a fraction of its total output rather than going offline entirely. The combining architecture provides both power scaling and redundancy that a single large aperture laser source cannot replicate within the space and weight constraints of a naval installation. Coherence is what separates a weapon from a heat lamp, and the physics of that distinction is specific. An incoherent light source, a spotlight, a floodlight, any source without phase alignment across its output aperture, spreads as it propagates. Intensity falls as the inverse square of distance. Double the range and intensity at the target drops to 1/4. A coherent laser beam maintains phase alignment across its aperture, and that alignment preserves the beam's focus at range rather than allowing it to disperse. At 1 kilometer, but the difference between a coherent and an incoherent 30 kilowatt source is the difference between a spot approximately 10 centimeters across, close to the diameter of a large coin, and an illuminated area spread across several square meters of target surface. Power density measured in watts per square centimeter is what causes thermal damage. The 10 centimeter coherent spot at 30 kilowatts produces approximately 38 watts per square centimeter, enough to bring carbon fiber composite to structural failure temperature in 2 to 5 seconds, depending on layup and thickness. The incoherent equivalent spread across several square meters produces less than 1 watt per square centimeter, which cannot raise any drone airframe material to failure temperature within any operationally relevant engagement window. On a fiber laser system at 30% electrical to optical efficiency generates approximately 70 kilowatts of waste heat for every 30 kilowatts of useful output. That heat deposits into the gain fiber, the combining optics, and the structural mounts of each module. Too little cooling and the gain fiber temperature rises past the threshold where stimulated emission efficiency begins to collapse. The amplification process that builds coherent light through the fiber loses its gain, beam quality degrades, and the output transitions from a focused weapon to a dispersed source incapable of lethal power density at range. Too much cooling system mass and the ship's available weight and power allocation is consumed by thermal management hardware rather than by additional laser modules. See holding total output below the threshold required for reliable kills at operational engagement distances. The fiber coils sit in their bays in continuous wound loops, cooling lines running in direct thermal contact alongside each gain fiber section. The system runs its cooling circuits continuously, even between engagements. The pumps cycle at a low, steady frequency, the only audible indication in the laser bay that the system holds 30 kilowatts of potential output in those motionless coils. Individual fiber temperatures are monitored at every mounting point. Nothing moves visibly. The weapon at standby sounds exactly like a server room. Generating the power is not the hard part. The hard part is getting that power to the target without the air between the ship and the drone destroying the beam before it arrives. At 30 kilowatts, propagating through 1 kilometer of maritime air, the first atmospheric effect the beam encounters is thermal blooming. The beam heats the air along its path, and heated air has a lower refractive index than the cooler air surrounding it. The beam refracts outward, bending away from its own heated channel in a spreading pattern that compounds with beam power. At operational levels through 1 kilometer of maritime air, blooming can spread the spot from 10 centimeters to 30 or more, a 9-fold reduction in power density that extends a 2-second kill to 18 seconds. Against most threat drone attack profiles at close range, 18 seconds is not a window the engagement geometry allows. At 30 kilowatts through 1 kilometer of maritime air, thermal blooming alone can spread the beam spot from 10 centimeters to 30. That 9-fold reduction in power density is the difference between a weapon and an expensive flashlight. Thermal blooming is the first problem. It is not the hardest one. Atmospheric turbulence operates on a different physical mechanism and compounds the blooming effect rather than simply adding to it. The atmosphere is not a uniform optical medium. It is a continuously evolving volume of air cells at different temperatures and humidity levels, each one presenting a slightly different refractive index than its neighbors. A beam passing through this structure encounters thousands of small refractive discontinuities along its path. Each one deflects a portion of the beam wavefront by a small random angle. But the cumulative effect of those deflections across 1 kilometer of maritime air is not a simple spot enlargement. It is a distorted, partially coherent illumination pattern at the target that bears little resemblance to the focused spot the combining optic produced at the aperture. The severity of this distortion is characterized by a parameter called the fried coherence length, the distance over which the atmosphere can be treated as optically uniform. Over maritime air at low altitude, in the temperature and humidity conditions common to shipboard operations, the fried coherence length can be as short as 3 to 5 centimeters, roughly the width of a human hand. That measurement means the atmosphere is producing independent optical distortions at spacing smaller than the beam diameter every few centimeters along the entire propagation path. An uncompensated beam propagating through 1 kilometer of maritime air at these conditions arrives at the target with the effective aperture of a system many times smaller than the physical aperture that launched it. The power is present. The coherence that concentrates it is not. Adaptive optics solves this by measuring the distortion and removing it before the beam enters the atmosphere. The deformable mirror sits in the beam path before the output aperture, a reflective surface divided into individually actuated segments, each one adjustable in position by fractions of a micron under electronic command. The AN/SEQ-3 system's deformable mirror carries actuator counts comparable to the number of keys on a full concert piano keyboard, each one independently controlled. The mirror's surface is continuously reshaped to impose a pre-distortion on the outgoing beam that is the conjugate of the atmospheric distortion the beam will encounter on the way to the target. The atmosphere then undistorts the beam as it propagates, and the spot arrives at the target with the coherence and focus the aperture was designed to produce. The adaptive optics system is correcting for distortions the beam hasn't encountered yet. It is pre-distorting the beam so that the atmosphere undistorts it on the way to the target. That correction requires a continuous measurement of the atmospheric distortion between the ship and the target, and updated faster than the atmosphere changes. The wavefront sensor accomplishes this by analyzing the return from a reference source. either a low-power laser guide beacon projected along the engagement path ahead of the main beam, or the thermal emission from the target itself at close ranges where the target's own heat signature is bright enough to serve as a point reference. The wavefront sensor analyzes the phase distortions in the reference return and generates the correction commands for the mirror actuators. The coherence time of maritime atmospheric turbulence at low altitude is approximately 1 to 5 milliseconds. The atmosphere at sea level changes its optical structure on that timescale. The correction loop must run at kilohertz rates to stay ahead of the distortion evolution. And too slow, and the mirror is correcting for atmospheric structure that has already changed, applying corrections that worsen beam quality rather than improve it. Too fast, and the actuators cycle through their full range of motion faster than the mirror substrate can mechanically follow, accumulating fatigue in the actuator drives that produces a permanent surface deformation no correction signal can remove. The corrected beam exits the aperture and reaches the target with its intensity preserved. The fire control system now has to hold it there. A drone flying at 100 knots at 1 kilometer range presents an angular tracking problem. At that range and speed, the target moves at approximately 0.05 degrees per second in the beam director's reference frame, a rate that sounds trivial until the ship underneath the beam director is simultaneously pitching and rolling in response to sea state. A destroyer operating in sea state 4 experiences pitch motions of several degrees at periods of several seconds. Those motions are low in frequency but large in amplitude, and every degree of ship pitch moves the beam director's aim point by 1 degree in the target's reference frame. The beam director's main gimbal continuously cancels ship motion while simultaneously tracking the target's own angular movement, 2 separate motion profiles superimposed, both requiring correction at different rates and amplitudes to keep the beam on the target. The engagement display in the Combat Information Center shows a thermal image of the target centered in the tracking reticle. The aim point marker sits on the brightest thermal region of the drone's underside. The battery pack, visible as a distinct hotspot against the cooler airframe. The beam-on indicator activates. The dwell timer begins counting upward from 0 in tenths of a second. The gimbal moves continuously in small, rapid corrections that are invisible on the display but present in the data feed, updating 10 times per second. The ship pitches 2 degrees to port. The beam director corrects before the display registers the motion. The aim point marker does not move. The laser's advantage over a missile is not speed. A missile is already fast enough. The advantage is that the laser never runs out. The fire control computer does not aim at the center of the drone. Aiming at the geometric centroid of the target distributes the beam's energy across the widest possible area of the airframe, maximizing the time required to raise any single component to failure temperature. The system analyzes the target's thermal and optical signature continuously during track, and designates an aim point at the specific component whose thermal failure kills the drone in the shortest dwell time. A commercial drone's lithium polymer battery pack is visible in the infrared as a distinct hotspot. Higher temperature than the surrounding airframe even at standby power draw, clearly localized and thermally isolated from the rest of the structure by the foam and plastic housing that was never designed to conduct heat away from the cells. The flight controller is identifiable from its structural position and thermal output. The motor mounts are resolved from the optical outline. The system selects the aim point before the beam activates and updates the designation continuously during the engagement. Aim at the structural frame and the kill requires burning through carbon fiber composite to the point of mechanical failure, a slower process, more dwell time, higher probability of losing track before the kill completes. Aim at the battery and the laser does not need to burn through anything. The jitter budget that governs how precisely the beam must be held on that aim point is unforgiving. At 1 kilometer with a 10 centimeter beam spot, the total allowable pointing error across all sources, ship motion residual after gimbal correction, gimbal mechanical error, and vibration from the ship's propulsion and combat systems is approximately 50 microradians. 1 microradian of pointing error at 1 kilometer moves the beam spot by 1 millimeter. 50 microradians moves it 5 centimeters, half the spot diameter, enough to walk the beam off the battery aim point and onto the adjacent airframe structure where the kill mechanism is slower and the required dwell time doubles. The main gimbal removes the large amplitude, low-frequency ship motion. What remains after gimbal correction is a residual jitter at higher frequencies. The ship's engines, the laser system's own cooling pumps, acoustic energy propagating through the hull, that the gimbal's mass prevents it from tracking. The fast steering mirror handles this residual. Mounted in the beam path close to the output aperture, its small mass allows it to respond to correction signals at kilohertz rates, faster than a camera flash duration per correction cycle, removing the high-frequency jitter the main gimbal cannot follow. The beam arrives at the battery aim point with its spot position stable to within the jitter budget. The thermal process begins. The drone doesn't know it's being engaged. There is no warning seeker tone, no proximity fuse arming, no intercept to outmaneuver. There is only the temperature rising in the battery cell until the chemistry makes the decision for it. Carbon fiber composite fails in sequence rather than catastrophically. The laser first heats the epoxy resin matrix between the fiber layers, a material with low thermal conductivity that reaches its glass transition temperature at approximately 120 degrees Celsius. At slightly above the temperature of boiling water, at which point it transitions from a rigid structural binder to a softened material incapable of transferring load between fiber layers. The airframe does not burn at this stage. It loses the matrix integrity that gives the fiber its structural properties. A drone wing that has reached matrix glass transition temperature fails under aerodynamic load even if the laser dwell ends before ignition. The fibers are present, but unbound, and the aerodynamic forces the drone generates in flight complete the structural failure without further energy input from the beam. The battery aim point produces a different and faster failure sequence. Lithium polymer cells enter thermal runaway when cell temperature exceeds approximately 130 to 150 degrees Celsius, an initiation threshold only marginally above the boiling point of water, reachable by a 30 kilowatt beam on a battery-sized aim point in under 2 seconds at 1 kilometer. At that temperature, an exothermic decomposition reaction begins within the cell chemistry that generates more heat than the laser is delivering. The runaway propagates through the battery pack autonomously. The laser does not need to maintain dwell after runaway initiates. The kill is self-sustaining. The flight controller loses power as cell voltage collapses. The motors lose their control signals. The drone departs controlled flight. The airframe begins to deform asymmetrically as the battery pack temperature climbs past 200 degrees and the surrounding structure loses matrix integrity. One motor arm droops as the resin at its root softens. The flight controller issues correction commands that the motors cannot execute because the geometry they were calibrated for no longer exists. The drone rolls, pitches, falls. The Combat Information Center display shows the thermal signature tumbling and dropping below the tracking gate. The beam-off indicator activates. The dwell time logged is 2.3 seconds. The missile that could have engaged that drone cost between $500,000 and $1 million. The drone cost approximately $500. The laser engagement cost approximately $1 of shipboard electricity. That arithmetic is not incidental to the weapon's value. It is the weapon's primary operational argument. A destroyer carrying 24 surface-to-air missiles can be saturated by a coordinated swarm of 25 drones, each costing less than the fuel burn maneuvering to avoid them. The laser's magazine is the ship's electrical generation capacity. Against sequential targets, it engages, kills, and returns to ready state in the time a missile crew is completing a reload. The thermal management system accumulates heat load across sequential engagements and requires a cooling interval after approximately 10 rapid kills, a constraint that matters against a 30-drone swarm and defines the boundary of the system's current limitation. The laser does not replace the missile. It handles the volume of targets the missile cannot economically address, and the Navy's drone problem is a volume problem. The weapon that costs $1 per shot will be fired at targets that cost $500. That exchange ratio does not require the laser to be faster, longer ranged, or more lethal than a missile to make it the correct weapon for this threat. It only requires the atmosphere to be solvable. It is.